So let's welcome Joseph Farah.
Yeah, and I just want to say another big thank you to Andy. He's an amazing supervisor, and it's a really privileged to get to work with him and the LCO folks. Thank you all for coming out tonight. Especially, I know some of my students are in the audience, and the professor I TA for. You guys are awesome. I'm left-handed, so I should have done this from the start. So tonight I want to talk to you guys about the Black Hole Explorer, which is this collaboration that I'm a part of to build this telescope, which I'm going to tell you all about. But first I want to tell you about this incredibly strange object fairly close by. So 25,000 light years away from us sits one of the most exotic and mysterious and bizarre objects in the universe, which is a supermassive black hole. And 25,000 light years sounds like a lot, but it's not. Trust me, if a supernova went off 25,000 light years away, we'd be very excited. So, the black hole in the center of our Milky Way is this thing called Sagittarius A star. This was the EHT image that we took in 2017 and then published in 2022. And these black holes are just incredibly weird. So for one, they're very large. So this black hole in particular is on the small end, and it's still over 4 million solar masses. And all of that is crammed into an area smaller than the orbit of Mercury. So this thing is bigger than some solar systems, millions of times more massive than the sun, but under general relativity, it's this incredibly large and complex object is only described by two quantities: how massive it is and how fast it's spinning, its angular momentum. Now, we really want to be able to measure these things. And right now, we have a really good ways to measure the mass, many ways, including this image. You basically just place a ruler on the image and measure how big the ring is, and that gives you a mass. But we don't have really any ways to measure angular momentum of these black holes. We have a couple ways, but none of them give the same answer. But we really want to know the angular momentum, the spin of these black holes, because if you don't know how fast a black hole is spinning, you basically don't know half of all the things there is to know about it. So it's kind of important to know how fast the black hole is spinning. And if we can measure black hole spin, there's all sorts of stuff we can do. If we measure black hole spins across the universe, and we see that most of them are spinning very fast, this tells us that they're spinning up via accretion. So they grow via sucking things in. The energy of the things they're sucking in contributes to how fast they're spinning, and they spin faster and faster until they approach their maximum spin. But if we survey a bunch of galaxies, a bunch of supermassive black holes across the universe, and find out that they're spinning very slowly, then it tells us actually that the dominant growth mechanism for these things is probably a galactic merger. So these things may accrete and spin fast, but over time they collide when they and their galaxies crash together, and they lose angular momentum from these collisions. So, with each successive attempt at imaging black holes, we've gotten to zoom closer and closer. So, we had these incredible movies made of the stars orbiting the black hole in the center of the Milky Way that we used to measure its mass, and then we zoomed in with the Event Horizon Telescope and made the image, the best image anyone's ever made of a black hole's shadow, which is the lack of light that's cast on the surrounding accreting matter due to the fact that there's an event horizon hidden somewhere under there. And so what happens if we peek even closer? Well, we have some thoughts. So we make these big simulations. And when we watch them evolve, these all have different simulation parameters, but the interesting thing is they don't really look that similar. They look all chaotic, and each one kind of looks like it has its own thing going on. But if you average out these simulations over time, something very curious emerges. All those minor, short timescale fluctuations go away, and we're left with this incredibly thin and impossibly bright ring called the photon ring. And this photon ring is a super fascinating feature. It's created from photons that are violently adjusted by the black hole's gravity, forced to orbit it multiple times. And as a result, they form this incredibly thin ring on the image, which is actually more than just a ring. It's an infinite series of subrings corresponding to how many times each photon had to orbit around the black hole before it reached our eyes. And this is really important because photons are the thing that can get closest to the event horizon of a black hole, which is what we're interested in. They go right down the barrel and come back out and form these rings. So they, in a sense, are a probe, the last stop on light's journey before it reaches the event horizon. And now, the event horizons of black holes, conventionally we know what they represent, right? Intuitively. what's inside never comes back out. And what's outside, you don't want to be inside. But this horizon is more than just a boundary between in and outside the black hole. It's something much deeper than that. In a sense, it's a boundary of our universe. What's outside the black hole is inside of our universe, but anything that's inside the black hole is outside of our grasp forever. Whatever goes in there never comes back, and in a sense, every black hole represents a boundary, horizon, beyond which is the unobservable universe. But it's even more than that, because inside of these objects, we don't know much. We have these two theories that describe how the universe works: general relativity and quantum mechanics. General relativity tells us about things that are really, really large, and quantum mechanics tells us about things that are really, really small. But a black hole is kind of both of those things, right? It's a hugely massive object squeezed into a very small space. And the really interesting thing about these two theories is that they have never, ever been proven wrong. Over the last century, we have done experiment after experiment after experiment to obscene levels of precision, and these two theories are never incorrect. When we thought they were, it turns out we were wrong, and we had to fix something. So when we ask these two theories, what's going on in the center of this thing, it tells us, they both tell us different answers. So one of them is wrong. And if it's general relativity, that's really bad. If it's quantum mechanics, that's so much worse. So the event horizon is not just a boundary of the universe or just the inside and outside of the black hole. It's a boundary between what we know, because we know pretty much what's going on right up to the edge, and then right after, we've got no clue. And so it's a boundary into new physics and what's next. That's what the photon ring represents. It's the last stop on the only probe that we have into this incredibly strange region of the universe. So needless to say, we really, really want to take a picture of the photon ring of a black hole, and we haven't yet. So if we want to take a photon ring of a black hole, take a picture of the photon ring of a black hole, what's that going to take? And is it even possible? And to kind of dive into that, we need to talk about how telescopes work real quick. So basically the way a telescope works, it has this thing called its resolution, which is how small of a thing it can see on the sky. And its resolution is basically just a function of how big it is. So if you want to see something smaller or farther away, you just get a bigger telescope or build a bigger telescope. But there's a limitation to this. We've tested that limitation a lot. We push our telescopes to be 30 meters and bigger, but we can only build our telescope so big. However, if you link two telescopes together via something called interferometry, which is a magic process that no matter how long I work on it, I will never fully understand, the resolution is no longer a function of the size of the individual stations, but rather a function of the distance between them. And this leads to an immediate life hack. You don't need to build a telescope as big as the Earth. You just take two small telescopes and place them on opposite sides of the globe, do some voodoo, and now they're an interferometer and have stupidly good resolution. So how stupidly good are we talking? So to give you some context, the resolution of the human eye is 1 arc minute. So if you're one of the very few people that doesn't know what an arc minute is, that's a joke because why would you know that? An arc minute, you can think of it like if someone holds up a credit card across a football field from you, you'll be able to kind of just barely see it, but not anything on it. That's about an arc minute, a credit card across a football field, and that's about the limit of what the human eye can see. You put on a pair of binoculars, and now your magnification increases 20 times. So your resolution goes from 1 arc minute to 3 arc seconds. So 20 times better resolution is afforded just by binoculars. Now we build these big telescopes, like the Hubble Space Telescope, to get unbelievable resolution, like 0.05 arc seconds, which is if you're sitting here, in this room, and you have the vision of the Hubble Space Telescope, you'd be able to see a credit card in Los Angeles from where you're sitting right now. That's how good the Hubble Space Telescope's resolution is, but that's peanuts compared to interferometry. So one of the earlier images of Sagittarius star was created with this thing called the Global Millimeter VLBI Array. It put 2 stations halfway across the world and achieved a baseline length of 8,600 kilometers, which gave it a resolution of 100 micro arc seconds, 500 times better than Hubble. And Sagittarius star, the black hole in the center of our Milky Way, still just looks like a blurry blob at that resolution. So it took the Event Horizon Telescope, which literally placed telescopes as far apart on the Earth as they could possibly go, one in Greenland, one at the South Pole. It took that to resolve the shadow and see the shadow of the supermassive black hole in the center of the Milky Way for the first time. It achieved an incredible 25 micro arc seconds. But you can't get farther north than Greenland, and you can't get farther south than the South Pole. That is an Earth diameter interferometer. So where do we go from here? And that is where the Black Hole Explorer was born, a radio telescope in space that will take the first image of a black hole's photon ring. So since 2019 and 2020, we've been building up this collaboration. We're working with the Jet Propulsion Laboratory and Lockheed Martin to build the spacecraft. We have a huge team of people from 15 institutions all over the world on every continent. And it's all this one collective effort with one goal in mind, to see the photon ring of a black hole for the first time ever and measure its spin. And that's me in the back there. You need Hubble resolution to see it, but So with the Black Hole Explorer, right, remember the Earth's diameter is 12,000 kilometers. With the Black Hole Explorer linking up to the Event Horizon Telescope, we would achieve a maximum baseline length of 26,000 kilometers, giving us a resolution of 3 microarcseconds. It would bring our black hole images from this to this. And it would allow us to see a black hole's photon ring for the very first time. Nice! We made it so far without the presentation crashing. I want to talk to you guys real quick about some of the technological challenges of building a telescope like this, because I can't talk to you about the science because it's going to launch in 2031. Hopefully, JWST comes to mind. We're going to try to not do that. One of this telescope, it's hard to overstate how insane of a technological challenge building a telescope like this is. It's already hard enough to do interferometry on the ground. One of the challenges of interferometry that will extend very much so to space is the technological challenge of that the stations of an interferometer needs to know its location in space and time extremely precisely. So we measure the distances between our sites in wavelengths of a photon. And we need to have precision location down to that value, basically, in order to accurately make measurements. And our sites are so good at knowing their location that the United States Geological Survey uses the Event Horizon Telescope stations to monitor tectonic plate drift, because we know our position so well that if it changes a couple millimeters, we'll know. And on top of that, we need to know exactly what timestamp, at exactly what time data we're taking, because we're going to take all the data from these telescopes and combine them back together into a huge one. So it needs to know its times. It needs to know these times down to nanosecond precision. On the ground, we use these things called hydrogen maser atomic clocks. They use properties of the hydrogen atom to measure time down to the nanosecond, and they are really fragile. I almost broke one when I sat on a box that contained it. There's a really funny story from one of our observations where, we had this whole thing, multiple stations around the world keyed up, all looking into the sky at the same time. And then one of these things broke at one of the sites, and like a fan broke, it needs to stay very cold. And we had to tape a door open because the nearest engineer was 40 miles away. And the whole observation was relying on whether the tape would hold the door open long enough for the observation to continue and not overheat the device. So needless to say, putting one of these things in space is going to be an act of God. So, but we need to in order to make these kinds of measurements, and we will, and we're working on it. So another technological challenge involves the data. There's so much data involved with these kinds of experiments. So the Event Horizon Telescope, per night of observing, is the largest, records the largest amount of data of any experiment in physics history, period. In one night of observation, the Event Horizon Telescope records 1.5 petabytes of data. So your phone probably has a couple hundred gigabytes of storage. A terabyte is 1,000 gigabytes, and a petabyte is 1,000 terabytes, and that's one night. Throughout a whole observation, we record something like 5 petabytes. Needless to say, we cannot store this on board the spacecraft because we can't get it back down, easily, without burning up in the atmosphere, I guess. And there's another problem, even if you do store a lot of that data up there, it's going to get corrupted by cosmic rays, and that's going to cause all kinds of issues. So we have a different solution. We worked with some folks at Lincoln Labs and developed a face-meltingly strong laser that will beam the data back to Earth at 100 gigabits per second. So basically no storage needs to be maintained on board the spacecraft. There's going to be one of these optical downlink terminals in every time zone, and the BEX telescope will fly around, and as it collects data, it'll just beam it straight to the ground, and hopefully not evaporate any citizens. So, let's just say it's real life. Yeah, most of our funding comes from the military applications of the Bex spacecraft. I'm hanging out with Moira and Ethan too much. So another issue is, let's say all this, by some miracle, all of this works, okay? And it will, I have faith, and we're working on it real hard. But let's say all this works. We still face another problem. The data is gonna be pretty hard to work with. So what I'm showing you here, don't worry about like what's really going on, but basically you see there's two regions of data. There's one that's really nice and clean and sharp, and there's another that's like substantially less so. Unfortunately, the clean, sharp region is the part we don't really care about that much. We already took images of that, and we know how it works. We got it, we know so. The part we're interested in, the n=1 photon ring, which is this one up here, that's where all the noisy stuff is. And we have to pick that apart and find a pattern similar to this bouncing behavior. And that's really, really hard. So that's one of the problems that I work on actively, is methods to analyze the behavior of the photon ring and understand how we can exploit patterns and the underlying physics in order to extract these features from our images and train machine learning models and perform geometric analyses in order to make, not just make a measurement on the photon ring of the black hole spin, but to confirm that there's even one there in the first place. If there's not a photon ring there, that would be a physics-shaking discovery. And so the stakes to make sure that this object is in fact there are unbelievably high. So thank you so much for listening, and look forward to the Black Hole Explorer launching in 2031.
Thank you, Joseph. And by the way, he's kidding about the face melting laser.
Yeah,
I mean,
that's wrong.
it is a laser, but it won't melt your face, and there are no military applications to the Black Hole Explorer. Of course not.
But it makes for a great joke,
As
right?
far as you know, yes.